Okay, you're on.
Okay, so hi everybody. So for our presentation, we focused on oceans and more specifically on the deep sea. So first, our essential question was, why does deep sea wildlife matter to the biosphere? How does climate change affect the deep sea? And lastly, how can we better preserve deep sea ecosystems? So before we actually talk about anything in regards to the deep sea, it's important to establish what is the deep sea. So the ocean is classified into 5 distinct zones. You have the epipelagic zone, which is commonly known as the surface. So any part where you can see light, that's the epipelagic zone. Mesopelagic zone is the twilight zone. At this point, sunlight does still penetrate into these depths. However, it is minimal to the point where photosynthetic organisms cannot live and thrive in this environment. Bathypelagic zone is the midnight zone, and the abyssal pelagic zone is like the seafloor. Lastly, you have the handopelagic zone, which is like trenches. For the sake of our presentation, we'll be focusing mainly on the abyss as well as the midnight zone. So some distinct features about these zones is that there's really, really high water pressure, as in the ocean, every 10 meters, the water pressure increases by at least 1 atmosphere. So the atmospheric pressure increases by 1 of those every 10 meters. So it gets pretty hard to do anything down there. Low temperatures is close to freezing at these depths, going around 39 degrees Fahrenheit or 4 degrees Celsius in the midnight zone, as well as an absence of light, as we've said before, with a less than 1% sun penetration.
Okay, so some facts about the deep sea. So fewer humans have explored the deep sea. The ocean's deepest regions that have walked the moon, so very few people have been down there. And then less than 5% of the ocean has actually been explored, so we know very little about it. And they're estimated to be around 10 million species in the deep sea, but many of them are unknown. So I'm going to talk a little bit about deep sea wildlife. So most species are slow to grow and reproduce, and they are highly adapted to the environment, which also means that they are extremely vulnerable since we know so little about them and the environment that they live in. This is an image of a Dumbo octopus, and it lives in the epipelagic zone. Okay. And then I'm going to talk about deep sea wildlife adaptations. So there are 5 different circumstances that deep sea wildlife have adapted to. So the first is light. So animals in the deep sea have very large eyes so that they can compensate for the absence of light, or they're blind and their other senses are enhanced. Many of them are bioluminescent, and scientists think that this bioluminescence has 6 different functions. The first is headlights, so that they can see, social signals, so that they can attract mates. They use bioluminescence to attract prey, and then they also use counter-illumination to camouflage, and they usually produce blue light exactly matching the faint sunlight from above, making them invisible from predators below. It's also used to confuse predators or prey, and it is used to alarm prey of incoming predators. And then bioluminescence is usually blue or blue-green because those are the colors that travel the furthest in the water. And then the deep sea animals also have membranes and proteins that are pressure resistant. This isn't fully understood yet, but we do know that the biomolecules do not work well under low pressure or shallow waters. They also use piezolytes, so this is basically when an organism has an optimal growth rate under a lot of pressure. And then next they have loose flexible proteins and unsaturated membranes in order to adapt to the intense cold. They also means that they will fall apart in higher temperatures. And then for food, they have large mouths, hinged jaws, fang-like teeth, large expandable stomachs, and they have other ways of preserving energy, such as not moving that much and having a lower metabolism. some other adaptations are body color, reproduction, gigantism, meaning they're a lot bigger than regular animals, and then they also have longer lives.
Okay, so now I'm going to talk about the deep sea biosphere, the deep sea in relation to the biosphere, and how I'm going to do that is I'm going to do a demonstration. Yay! So before we talk about the demonstration, there are some few concepts I will need to cover. Oh wait, I'm missing something.
You're missing your iPhone.
No, I'm missing
the string.
the string over there. Oh no. So whale falls are constituted as basically when a whale dies, its whole body sinks to the bottom of the ocean and brings 2 tons of carbon with it because due to the laws of gravity as well as because it can no longer move, it sinks. Yes, thank you. As well as marine snow, which is categorized as the continuous shower of small organic debris, such as decaying or dead animals, fecal matter, or silt sinking from the surface of the ocean downwards. So this is a density tower. Can everybody see it? And basically, as from you can see, if you look at it from the side, you can see there should be 4 distinct layers. So you first have the surface layer, then you have the midnight zone, then there's this really big part. No, you have the twilight zone, then you have the midnight zone, and lastly you have the abyss. So, as I open this up, as you can see, we will have this to simulate a whale. When it's alive, it usually is here. And the moment it dies, it sinks to the bottom. And it brings with it a bunch of carbon. It is estimated that a 40-ton whale carcass typically has 2 tons of carbon in it. And then this is marine snow. And as I pour it, you will see that it will sink to the bottom. However, some of the marine snow will get stuck in the in-between layers, as marine snow is a pivotal part of the food chain for deep sea organisms. So usually on their way downwards, it gets consumed by other animals and then starts the cycle all over again. Regardless, at some point, the marine snow and the carbon will sink to the bottom, and due to the laws of gravity and pressure, there's no way for the carbon fillings, or carbon for this matter, to go back upwards and get re-entered into the atmosphere, and that is why the ocean can be such an effective form of carbon storage.
So I'm going to talk about climate change's impact on the deep sea and the ocean as a whole. So anthropogenic influence is the changes to a biophysical environment and to ecosystems, biodiversity, and natural resources caused directly or indirectly by humans. So anything that we do that affects the environment, that's anthropogenic influence. So depicted here is the human industries that cause the most fossil fuel release into the atmosphere in 2020. So as you can see, the highest is transportation, like there are cars everywhere. Surprisingly, the lowest is agriculture, which I thought would be a little bit higher on the list. So to understand how we influence the Earth, we need to understand the global carbon cycle first. So a quarter of the carbon dioxide released into the atmosphere due to human interference is absorbed by the ocean. So this carbon dioxide intake is distributed. So some returns to the atmosphere, and a small amount gets processed in the surface levels of the ocean, like right here. And a lot is exported eventually, after a lot of time, to the deep sea, like where all those little CO2s are. Unlike the atmosphere or the surface, the deep sea can hold up to 50 times more carbon dioxide than what the atmosphere can. So as Andy said before, it's a really effective tool for carbon storage. Although largely unexplored, the deep sea is vital to the Earth's carbon dioxide regulation and significantly limits climate change's impacts on the Earth. So the oceanic chain of command in terms of carbon regulation begins with phytoplankton. It's right there, like they live in the surface. They are microscopic marine plants. There's many of them, so many, millions. The carbon dioxide that gets absorbed by the surface levels of the ocean is first processed by the phytoplankton because as part of their photosynthetic process to survive, they convert this carbon dioxide into carbon-containing molecules, otherwise called organic carbon. So only a tiny amount of this carbon makes its way to the deep sea directly from the phytoplankton because phytoplankton are at the bottom of the food chain and they help sustain other marine life. So a slightly bigger animal will eat the phytoplankton, a slightly bigger animal will eat that, and there's a whole process through which phytoplankton get consumed. So although the carbon does eventually reach the deep sea, it isn't organic anymore. As Andy said before, the organism, be it fish, whale, or even an organism's fecal waste, has decayed by the time it reaches the deep sea. And decay or rot causes carbon dioxide release, which counteracts its previous conversion to organic carbon. However, all carbon that reaches the deep sea is preserved and stored, perpetually isolated from the atmosphere. So anything we put down there, be it carbon, which is the main point of this presentation, it can't come back up. So stratification by itself means the vertical layering of a habitat. But in a post-climate change context, it refers to the increase of different oceanic zones due to global warming as they become more polarized. The surface layer has an average temperature of 17 degrees Celsius, while the deep sea averages at around 4 degrees Celsius. And each zone has different salinities, which means how much salt they have. Both of these factors contribute to a severe difference in density. For example, the cold causes water molecules to move slower, producing denser water that sinks to the bottom, which is why all the cold water is at the bottom. So this difference in density is what allows us to see distinct oceanic zones today, as the zones can't mix, just can't. However, global warming has increased stratification to an unhealthy degree. For example, the melting of icebergs inserts fresh water into the surface of the ocean, and after a process of heating, it helps melt other icebergs because now the surface layer is a little bit warmer. Since icebergs have no salinity, so they have no salt, an acceleration in global warming could mean that our oceans will have an added freshwater layer on top of the ocean that saltwater fish haven't acclimated to. They can't survive in that. So due to climate change, the zones still get warmer, even though they don't mix, and hotter waters, although appearing insignificant, reduce biodiversity and viable habitat spaces because of certain species' heat tolerance. So fish like tuna or marlin lessen in numbers due to their and their environment's heat tolerance. They can't handle that much heat, which in turn increases the population of calamari, their prey, which are really tasty, so I guess we can eat more. There's also an oxygen exhaustion factor to consider, and a decrease in phytoplankton, which are the very basis of many food chains. So phytoplankton additionally convert inorganic carbon into organic carbon that eventually serves as the primary source of food for deep sea organisms. So if everything dies on the surface, nothing will get to the bottom. So the entire ocean will just not be alive. So the differences in temperature and depth render stratification as an effective barrier between the functions of each zone, allowing them to communicate without comprising their own ecosystems. But with climate change comes the elimination of said barrier and an increase in zones, which would be catastrophic to all the animals living in each zone. And 90% of animals live in the surface layer, so their deaths would be detrimental. And these pictures are obviously really adorable. Like, look at their little smiles and like him like cuddling. But all of the links that these images had from the websites that they were from were about how much their populations are decreasing. Like this one was really sad. But these little happy images came from websites about climate change destruction. So like, think about that.
Okay, so now that we've talked about the effects of climate change on the deep sea, I'm going to talk about how we can preserve the deep sea. So there are three different categories that I'm going to talk about. So the first one is costs and benefits. So deep sea restoration has begun, but mostly in the UK. However, the effectiveness of the restoration efforts is unknown since we know so little about the deep sea and the deep sea ecosystem. And it's also extremely expensive to do, so that's why it's not really happening around the world. The next is global strategy. So from an article that I read, it suggested that there should be a taxation for polluters so that we can have a polluters pay mindset. And then another suggestion is that we have more legislation or regulation to protect the deep sea biodiversity and protect animals beyond deep sea fishing and mining. And then next is funding. So as I mentioned before, there should be a tax so that can fund this restoration process. And the website also suggested that there should be an international finance facility which would mobilize resources for deep sea restoration, and this would be funded by donations.
Okay. So, since not a lot is known about the deep sea, inadvertently we're not taught a lot about the deep sea. So some important things that we learned from our project is carbon storages, how that relates to the deep sea wildlife, and climate regulation. Because of course we know climate change is super important, but before we actually started this assignment, we knew little to none about how that would impact the overall ecosystem. Any questions? Mr. Prison?
What does deep sea restoration look like? Like, how does one, like you said, it's expensive and you should be paid by taxes, whatever, but like, what is it? Like, how do you do deep sea restoration?
Yeah, like, when I saw it, it's like, well, okay, first they're trying to explore the deep sea even more because you can't restore it without knowing the effects that you're going to have on the deep sea. So first we need to do a lot more research because in one of the articles that I read, they were trying to use like these chemicals to like try and find deep sea animals, but then it was like destroying the ecosystem. So then obviously that's, while you're trying to do research, it's also harming the environment that you're trying to explore. So it hasn't really been happening, but
Also, like Kate said, there's a lot of like deep sea mining and deep sea fishing for like exotic fish and exotic types of rock. So when people do that, they also destroy like carbon sinkholes that fish use as part of their ecosystem. And like, I don't know, if you mine down there and you like disrupt a whale carcass, like that whale carcass can last like 20 plus years to the fish down there.
Yeah.
So it would hurt their like amount of sustenance. And if you're looking to like research the deep sea, like websites, there's a project called like Station M, and they're like trying to map the deep sea. So if you're interested in that, you can just like search up Station M deep sea, and there's a lot of really cool stuff that they're doing.
Yeah, and like even exploring the deep sea is really hard because it's really expensive, and as I've said before, there's a lot of things in the deep sea that make it really hard to explore. Like the big thing is pressure. We have yet to fully understand it, and building things that can withstand that immense amount of pressure that just continues, because it's like every 10 meters, which is not that deep, so it means that it stacks up really quickly. So I think the main thing right now is research in order to understand it, and once you understand it.
Also, in some ways, to like add on to what you guys just said, like the very exploration of the deep sea is also hurting their ecosystems, because like obviously we need to explore it so that we can understand how to like help it. help their ecosystems, but like a lot of scientists, you know, they go down there and they take like, you know, blobfish, like everyone's seen that like meme of the like, melting like fish. When they're actually just like regular fish that live down there, and when they take that fish and they bring it up, the severe difference in pressure crushes all of their bones and their skin gets all like wrinkly and like melty.
Yeah.
So the very fact that we're like exploring the deep sea and like trying to bring things up is also disrupting the ecosystem.
Yeah, because they're so highly adapted to the environment. You can't really bring them out of the environment that they're adapted to. So they'll just die.
Yeah, and that's why we can't go in, because we're so adapted to this environment. So,
Yeah. Yeah.
And for the iceberg, two questions. The first is, why are the icebergs like freshwater? And also, why would the freshwater layer of the iceberg be on the top? I know like the Dead Sea, like body water, and then that like anything like saltwater float, and the freshwater like be like dispersed into the saltwater.
Icebergs are like breakage off of like the land itself. The land itself isn't salty. Like it's like it's been formed with different water than the ocean is from. So when the icebergs go out to sea, they're like completely freshwater. They have no salt, and because of climate change, they like melt and get into the water. But right now, the fresh water mixes with the salt water because there isn't that much of it. But once everything starts melting, there is a possibility that since the fresh water is less dense because it doesn't have salt in it, it'll sit above the surface layer with like a little like thin like film of like fresh water just like on it.
like this thing right here, it's like
Yeah, it'll look like that. Like that. That would just be the fresh
The
water.
whole reason why this is a density tower is the substances can't mix with each other and they sit on top of each other. So
They can't mix due to their different temperatures and their different salinities. But the ones that are the densest sink to the bottom, and the fresh water from the melting of the icebergs, like mixes into the surface, so it doesn't mix here. And it's lighter than all the other like saltier parts of the ocean, so it'll sit at the top and just like cut like. But that's when all the icebergs start like melting in very like rapid rates. But the more icebergs melt, the warmer temperatures, like the surface water that has gotten warmer because of climate change, it'll warm up the fresh water, so then they'll be like of equal like temperature, but their salinities are different, so that makes the fresh water less dense, so then it'll go sit on top.
Why doesn't the salinity like get diluted overall?
Because in like, it's like, yeah, sure, go ahead.
it's like if you have a cup, it's like when you cook, when you have a cup and you have something that's really salty, when you add water, you know how it tastes less salty. Salinity just is salt. So when you mix fresh water that doesn't have salt with salt water that has a lot of salt, the salt water mixes with the fresh water and leaves that the total mixture.
Yeah, that's right.
But like, it's like the other way around.
Oh,
But right now, they're mixing.
Yeah.
But eventually, the overall warmth, like the surface layer is getting warmer. When you have massive amounts of icebergs melting, they'll just start forming their own layer because now they don't like, they're less dense. They'll like, because right now there's
How thick are we expecting the layer to be?
the layer, like it's years into the future.
No, I understand that.
Oh.
I mean, are we talking about an inch of water? Are we talking about a foot of water? Are we talking about 3 feet of water?
It's not that thick. It's like,
Because you would think that with wave action, just the wind blowing, you would have
it's a
enough.
thinner film.
You would have like enough rollout.
Well, wind-driven upwelling is also like lessening because of climate change. So if we have less wind-driven blowing the ocean and more melting, then eventually we'll have like a thin. Right now, the freshwater is not enough for it to create its own layer. But once it has more of its like own kind together, they can like separate.
Thank you.
If that makes sense. Does that make sense?
Are there any other questions?
Yeah. what's up?
Do you guys like Olympic
Yeah. Although that whale sounds like it's gonna fall.
Because the funny part of the joke is the whale at the bottom of the sea. It's like, I can't tell you this up here, but if you go to the bottom of the sea.
Yeah. Also, I saw so many depressing images when I googled like